This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2018 AP Calculus exam, free response question AB5, namely L'Hopital's rule. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start with a little bit of background information, a few definitions, and I'll try to convince you of why we need another method to evaluate some limits. This will lead us to a formal statement of L'Hopital's rule, and we'll take a closer look at a special case in order to see some analytical and graphical evidence for the conclusion. I'll try a few examples, and I'll leave several for you, and I'll mention some other indeterminate forms and how L'Hopital's rule can be used in each case. Let's start by taking a look at a couple of examples that demonstrate the need for L'Hopital's rule. First, suppose we need to analyze and sketch a graph of the function f. Note that f is not defined at x equals 1. However, we still need to know how f behaves near 1, and that means we need to evaluate this limit. To find this limit, we first consider the limit laws. The limit of a quotient is the quotient of the limits. Here, as x goes to 1, the log of x goes to 0, and x minus 1 also goes to 0. So direct substitution leads to 0 over 0, which is an indeterminate form. This is an indication that we need to do something clever to evaluate this limit. So here's a definition. A limit of this form, where both of these limits are 0, is called an indeterminate form of type 0 over 0, and the limit may or may not exist. Now, we already have some solution techniques to solve limits of this type. If the quotient is a rational function, we might be able to cancel some common factors and then evaluate the limit. Here's an example. And a geometric argument can be used to find this limit. However, neither of these methods can be used to evaluate the limit in example 1. Let's take a look at another example in which the limit is not obvious, nor do other solution techniques help. Consider the limit as x goes to infinity of the log of x divided by x minus 1. Now, in this case, as x goes to infinity, both the numerator and the denominator increase without bound. If the numerator is increasing faster than the denominator, then the limit will be infinity. If the denominator is increasing faster, then the whole fraction goes to 0. And there could also be a compromise, in which case the limit will be some finite positive number. In general, a limit of this form, where both f of x goes to infinity or minus infinity, and g of x goes to infinity or minus infinity, is called an indeterminate form of type infinity over infinity. And this limit may or may not exist. Some limits of this type can be solved using existing solution techniques. For example, here we divide the numerator and the denominator by x squared, and then we can evaluate the limit to get 2/5. However, this method does not work in example 2. So these two examples suggest that we need another method to evaluate certain limits. Here's a formal statement of L'Hopital's rule, and I'll summarize by saying, suppose the limit, as x goes to a, of f of x over g of x is in an indeterminate form of type 0 over 0 or infinity over infinity. Then the limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of f prime of x over g prime of x, if the limit on the right exists, or is infinity, or minus infinity. Let's take a closer look at this rule. In words, L'Hopital's rule says that the limit of a quotient of functions is equal to the limit of the quotient of their derivatives, provided the conditions are satisfied. And it's very important to verify the conditions regarding the limits of f and g before using L'Hopital's rule. That is, we can only apply L'Hopital's rule if the limit is in an indeterminate form of type 0 over 0 or infinity over infinity. L'Hopital's rule is also valid for one-sided limits and for limits at infinity or negative infinity. So x going to a can be replaced by any of these symbols. I'm not going to prove L'Hopital's rule, but let's consider a special case. Suppose f of a equals g of a equals 0, f prime and g prime are continuous, and g prime of a is not equal to 0. We can show analytically why L'Hopital's rule is true here, and also illustrate this special case graphically. Because f prime and g prime are continuous, we can evaluate this limit. Then use the alternate definition of the derivative and a limit law. A little cancellation, and this proves L'Hopital's rule for this special case. This figure shows the graphs of two differentiable functions f and g, such that f of a equals g of a equals 0. As we zoom in near the point a0, both graphs are locally linear. This figure shows the linear approximations to f and g as we zoom in near x equal a. Therefore, near a, their ratio, the ratio of f over g, is the quotient of the linear approximations. Therefore, in this case, the ratio f of x over g of x simplifies to m1 over m2, the ratio of their derivatives. And this helps to confirm L'Hopital's rule in this special case. Let's try an example. Let's see if we can find the limit as x goes to 1 of the log of x divided by x minus 1. First, we need to verify the conditions in order to be able to use L'Hopital's rule. The limit as x goes to 1 of the log of x is 0, and the limit as x goes to 1 of x minus 1 is also 0. Now we can apply L'Hopital's rule. Take the derivative of the numerator and the derivative of the denominator and simplify. We can evaluate this resulting limit by direct substitution, and the limit here is 1. Here's a technology solution for this example and some graphical confirmation. Using the TI-Nspire, I can evaluate this limit directly. One might say simply that the calculator knows how to use L'Hopital's rule, but clearly there's a built-in algorithm that checks conditions and correctly evaluates this limit. And here's a graph of this quotient near x equal 1. I can trace along this graph and confirm numerically that the quotient is approaching 1 as x gets closer and closer to 1. In this example, let's consider the limit as x goes to infinity of x squared divided by e to the x. Again, first verify the conditions in order to use L'Hopital's rule. As x increases without bound, x squared goes to infinity, and e to the x also goes to infinity. So take the derivative of the numerator and the derivative of the denominator. There's no other simplification here. And if we try to evaluate the limit, again, both the numerator and the denominator are increasing without bound, going to plus infinity. So we need to apply L'Hopital's rule again. Take the derivative of the numerator and the derivative of the denominator. Now we can evaluate this resulting limit. The numerator is constant too, and the denominator is increasing without bound. So this drives the whole fraction and the limit here to 0. Now you might want to consider other similar examples, like the limit as x goes to infinity of e to the x divided by x squared, and other examples like this with various powers of x. This should lead to a general observation about the growth rates of power functions versus exponential functions. Here is a technology solution, and once again the TI-Nspire is able to evaluate this limit directly. And here's a little graphical confirmation of this limit. Even though I'm only looking in a very small window, it does appear that this quotient decreases rapidly as x increases without bound. Here are a few limit problems for you to try, and in each case, use L'Hopital's rule where it's appropriate. And if L'Hopital's rule does not apply, explain why. In part D here, m and n are fixed constants. L'Hopital's rule is a pretty amazing technique, but many limits may be determined using other, often simpler methods. So we can't forget all the other techniques for evaluating limits, and we should probably consider some of those other methods first before resorting to L'Hopital's rule. I just want to mention some other indeterminate forms and methods for evaluating these limits using L'Hopital's rule. These indeterminate forms are not tested on the AP Calculus exam. Suppose the limit as x goes to a of f of x is equal to 0, and the limit as x goes to a of g of x is equal to infinity, or minus infinity. Then this limit is an indeterminate form of type 0 times infinity. There is a numerical struggle here between f and g. If f wins, then the overall limit is 0. If g wins, then the answer is infinity or minus infinity. Or there may be a compromise in which the answer is a finite non-zero number. A technique for evaluating this limit is to rewrite the product as a quotient. For example, f of x over 1 over g of x. This converts the limit in an indeterminate form of type 0 over 0, and then we can use L'Hopital's rule. Or we could rewrite it as g of x over 1 over f of x, and this converts the limit to an indeterminate form of type infinity over infinity. And then we can use L'Hopital's rule. Suppose f and g are increasing without bound as x goes to a. Then this limit is an indeterminate form of type infinity minus infinity. And once again, there is a numerical struggle here. If f is increasing faster, then the limit is infinity. If g is increasing faster, then the limit is minus infinity. Or there could be a compromise. The limit could be a finite number. Now, this indeterminate form really represents two possibilities: infinity minus infinity, or minus infinity minus a minus infinity, a difference of like signs. And don't forget, we can replace x going to a with a one-sided limit or a limit at infinity. To evaluate this limit, we need to rewrite the difference in order to obtain either a quotient that yields the indeterminate form 0 over 0 or infinity over infinity, and then use L'Hopital's rule, or a product that yields the indeterminate form 0 times infinity. And then we'd need to rewrite the product as a quotient and use L'Hopital's rule. Now, this rewriting often involves a common denominator, rationalization, or factoring. And finally, there are indeterminate powers. Each of these indeterminate forms can be evaluated by first taking the natural logarithm of the function f of x raised to the g of x power, or by rewriting this function as an exponential function. Both methods will eventually lead to an indeterminate form of type 0 times infinity. And we know how to handle this indeterminate product. I hope this video provides some insight into L'Hopital's rule, a few AP Calculus type problems, and the use of technology to solve and visualize these types of problems. And just a reminder, There are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.